which is due today, and there I think I have to issue a small apology. Later in the class, at some point, I'll issue a major apology. I don't know when. But for this one, I have to issue a minor apology in that homework 1 actually had a little bit of material that we're not going to cover until today. So that was our miscalculation. But you have all the lecture notes and so on, so that's okay. So that's a minor apology. At some point in the class, I'll issue a major one, but who knows when. Okay. Homework 1 also, I guess, I think we never said anything about, I actually turn homework in and out. There's going to be an input port in Durand near my office. Or you could, I guess you could give them to the TAs. They're quite reliable. One thing you should know is under no circumstances should you give your homework or anything else important to me. Because, well, several things could happen. First of all, there's not even a reason, there's only an 80% chance your homework will even make it back to my office. Once it enters my office, it may not be seen for years. So, just a hint. Now that I've warned you, it's your problem if you give me your homework. That doesn't hold for the TAs. You just go ahead and happily give them the homework. So, I guess homework 1 is due, later today. I mean, we're not going to be very strict about this, but it's not due like, now, for example. Okay, so homework 2 is out, and you have that, and you have that now. And I think we're okay there. There we made a very careful effort to accurately estimate what we're going to cover and only put problems on that. So I think homework 2 we're okay on. The other thing is I want to remind you is that Friday, next class period, we have our first quiz. And I thought I'd say a little bit about this. Did you have those in 101? Did you have them in 101? Or? Every other week. Okay, so the difference is we kind of have them every week. So let me say a few things about the quiz and how that what the format is. The format is it's closed. Everything's closed. I mean, you just get the quiz, you do it. They're not a big deal. What they're supposed to be is it's supposed to be a simple problem that if you've been kind of following the material is easy to do. And the nice part about a quiz is it is not a problem to just totally blow one. You just kind of look at it and you say, I have no idea what they're talking about here, and that's fine. And that's sort of the idea. And then someone asked, well, gee, what would the quizzes look like? Well, I'm going to let you in on a secret. Pick up homework 2 right now. Here's your secret. Look at homework number 2. And if you want to know what a quiz looks like, I will show you some right now. Problem number 2, in fact, started life as a quiz. Okay? So that is exactly, problem number 2 was a quiz item. So was, for example, let's see, I think problem number 4, but don't quote me on that. Let's see. And problem number 8, well, which we just made up, would be perfectly appropriate for a quiz. Okay? So you can generally figure this out when you look through the homework if you want to know what the format of a quiz is. You look for a homework problem that's kind of very short, very snappy, the kind of thing you might be expected to do in 10 minutes. Doesn't require any old nasty calculations or anything like that. Then you're looking at it. So, okay, I think that's probably enough said about that. Okay, let's see. Any questions about last time? If not, we'll start. Okay, we'll start. So, last time we're just continuing our lecture on systems. Can you go down the pad, please? Can you go down the pad? Great, thanks. So here, just continuing our lecture on systems. Here's an interconnection which later is going to play a big role in this class and actually everywhere. And it's an interconnection of actually 3 systems, I suppose, if you're going to be very technical about this here. There's 3 systems here. There's an integrator, there's a scaling system, and there's also a summing or difference system right here, a difference system, I guess. After a while, you get so used to summers and things like that and difference things that you don't even consider them systems anymore. Okay? So let's write down the equations that characterize this. Well, that's easy. It says that y of t, that's this signal, which comes out of this integrator, is the integral of what goes in. What comes in is u of t minus a times y of t. So the equations representing this interconnection are exactly this. It's the integral of u of tau tau minus ay of tau d tau. And tau is just a dummy variable here. That's the integral up to time t is equal to y of t. Okay? So this here is actually a complicated integral expression relating y and u. It's an integral equation that relates y and u here. And so this equation is completely equivalent to this block diagram. These are just absolutely identical. From this, you write down that. From this, you write down that. Okay? Here, now here, it's not as simple for me to solve and express, say, y as a function of u. Okay? To do that, I have to solve an integral equation. Now, as a matter of fact, we'll be able to solve this particular integral equation by the end of next lecture. Okay? So it's not that big a deal. But it's not simple. It's not simple. You can't simply write down what is the expression. Now, that is to be contrasted with the previous example here. This is an interconnection of a bunch of systems, and we were able to explicitly and analytically write down what the output was in terms of the input u, this input n1, and this input n2. We were able to analytically write that down. Here was an expression. So here's an example where, at least at this point in the course, we cannot analytically write down what the solution is. Okay, so we have this integral equation, and systems like this are going to come up many, many times. And so it's probably worthwhile for you to see a simple trick, which I'll show you right now. The trick is this. If what's coming out of an integrator is y, then y is the integral of this signal here. Okay? So then I ask you, what is that signal? Well, that's it. So what signal is it that when integrated gives you y? It's y prime. That's exactly what it is. So when you see an integrator and and a signal y or any other signal comes out the output of an integrator, then you can immediately say that what went in is in fact the derivative. Now, if you think carefully about what you're doing, it means that you're really figuring out what the inverse of this box is, right? What comes in is y prime, well, sorry, what comes in is some signal, what comes out is y of an integrator, and we're saying, well, you happen to know the inverse of an integrator. That's differentiation. And so it tells you that if you go backwards, that tells you what went in. Okay? So that's sort of the idea. I mean, this idea applies to many systems. It's just not, maybe it's less obvious here. So if I do that, I point out that that's y prime. Then I say, well, look, y prime is the output of a difference. So what I see is that, in fact, y prime is equal to u minus a times y. And so I can also write down y prime equals u minus ay. Okay? So this is a differential equation. In fact, this differential equation is identical to this one because you just differentiate both sides of this and you get this. Okay? So they're identical. So what this says, it's not surprising, of course. If you can write something as an integral equation, you can often differentiate it and then write it out as a differential equation. And so these two are equivalent, and they're just different ways to do this. Okay, so that's this very common thing. As I said, we'll be able to analyze this very soon and completely. Okay, last topic for this lecture is differential equations. So, how many people here have had, what is it, Math 130 or something like that? Do we still require it? We've been trying to dump it for years. I think we finally did this for EE. And actually, for most of you, that means that is Math 130 still a class for EE? Yes. Boy, are you lucky. You should go find some friends who are taking Math 130 and ask them about it. Then you come back and thank me and the other people who dumped it for the EE requirements. Okay, so, but how many people have seen differential equations? Okay, where? Which one? Perfect, great. Okay, so differential equations. We'll do it again. It's fine. Actually, we're going to do special ones. We're going to do linear constant coefficient differential equations is ones we're going to look at. Okay, so turns out these differential equations, well, it's kind of a combination, and I'll tell you the truth in a minute. It's a combination of these differential equations come up a whole lot. That's observation number one. Observation number two is also that it's going to turn out we'll know everything about how to solve these differential equations. And in fact, by the time the course is over, differential equations like this will mean an enormous amount to you. Okay, so that's a lot of the course centers around this. I mean, by the end, you'll even have all sorts of good intuition. I could write in numbers here, specific ones you'll be able to glance at it and say, give a rough idea of what it is, or describe a physical system that is governed by these equations, and even have a rough idea of what it means and all that kind of stuff. So in fact, that's actually one of the themes of the class, are these types of equations. Okay, so it's called a linear constant coefficient ordinary differential equation, because what it's really saying is some linear combination of one signal, y, which we can think of as an output, but of course if you look at this carefully, you'll realize it's completely symmetric with respect to input and output. Who's to say what's the output and what's the input? Here it's a linear combination of derivatives of the output is equal to a linear combination of derivatives of the input. Okay? So the coefficients here they're not functions of time. They do not vary with time. They're numbers, like A1 is 3. Okay? So they're not signals. The y's are signals. Y is signal. U is a signal. Okay? The a's are constant coefficients, right? It's called linear because you don't have any products of the signals, and you don't have any squares of the signals or cosines and sines, this type of thing. Okay? So that's why it's called a linear constant coefficient ordinary differential equation. And we should probably find a better, some kind of better acronym than that, but that's what we're stuck with for the moment. Okay, so to say what to fully describe the system, you also have to give it initial conditions. In other words, it turns out, as you might or might not know or remember from your differential equation exposure, there's actually a lot of y's and u's that actually satisfy this equation. Hey, I wonder if maybe I should say something about this in general. Why don't I just say a little bit about differential equations and what the point is, actually. It is actually one, the importance of differential equations at a very, very high level is this. It's probably one of, if you made a list of like 10 unbelievably important ideas, like say from 1500 to today, differential equations would be there. Now you would never know that taking it in the math class, in your math class, okay? But here's the reason why. It's very, very interesting. And it's actually very profound. Here's the observation. I'll just take 1 minute on this. This is just sort of like cultural enrichment, okay? Here's the basic observation. You go back and you look at something like astronomy, or you look at the motions of planets, or you look at the motions of an object or something like that, of some mechanical system, right? And of course what you want to do is explicitly describe how it evolves. So when you fire a shell in, a cannonball in 1450, you want to describe it. And so you figure out that it's approximately a parabola or something like that, okay? So you write this down, and everyone wants it. Everyone prefers to have like an analytical solution of it, or something. If you have two bodies, that one planet goes around another, and it travels in an ellipse. Okay, that's fine. Okay, great. Of course, that's what you'd want. In fact, that's what you think of as the solution. If someone says, if I fire a cannonball and there's no air resistance, which of course is nonsense, then it will follow a parabolic orbit. A parabolic trajectory. And you can calculate now your firing angle and all this kind of stuff. And okay. Or you can calculate, for example, where the moon's going to come up tomorrow and all this kind of stuff. All right. Now, that method is very powerful. It's great. That's why we have, that's science and all that. It's wonderful. Here's the problem. It turns out that even very, very things, only a handful of things have analytical solutions like that. It turns out that, for example, as just a very simple one, if you actually want to know the exact solution of what happens when you have 3 bodies just attracted by gravity, what happens? Well, all the geniuses through hundreds of years tried to figure this out. And they knew, look, if there's 2, you have an exact solution, and there's an ellipse, and there's the center of mass of the 2, and analytically all this. Or here's another example. If you fire a cannonball in 1450 or something like this, and there's air resistance, it's no longer a parabola, of course, because when the thing first comes out of the can, it's going very fast. There's a very strong force pushing back on it, so it slows down, and it does not follow a parabola. Okay. So the question is, well, what formula does it follow if it's not a parabola? And the question for the 3-body problem is, what happens if you have three bodies attracted by gravity, right? And everyone assumed, well, there's a formula. Well, guess what? If there's a formula, I can tell you this, people don't know it. Okay, there is no formula. So in fact,
The observation, which was made basically by Newton, was unbelievably profound. And the observation was this. The observation was, forget the formula. That we're not going to describe what happens with three bodies in terms of an explicit formula. We won't describe what happens to a cannonball when fired in terms of a formula. It turns out, he said, we're going to have to relax our idea of what we call a solution. It turns out in both cases it's extraordinarily easy to write down a differential equation that tells you how three bodies evolve. It's extremely simple because, well, you write down the differential equation. The acceleration of each body is, is the force on it divided by its mass. That's a differential equation. Okay? How a cannonball actually goes through the air and stuff like that is given by a very simple differential equation. We could write it down right now. It's very simple. Okay? So the observation was, I guess from a philosophical point of view, that for a lot of dynamical systems, these are dynamical systems, there will not be, and it's not easy to write down an analytical solution. But for almost all dynamical systems, it's extremely easy to write down a differential equation that describes the system. Now that's actually philosophically very, very interesting. The formula says, here's an explicit formula that tells you where the cannonball will be 12 seconds in the future. Here's an explicit formula that says what the configuration of 5 planets will be in the future. We can't do that. What we can do, though, is we can say things like this. If the planets were in this configuration, I can tell you which way and in what direction and how fast each one is moving. That's a differential equation. Okay? So I think I took more than my 2 minutes, but not much more. Okay? So this is, I just want to point out, although when you learn about differential equations, it is usually profoundly boring. It is, in fact, one of the, it's on that list of 10 of the most profound ideas in the last 500 years. Differential. Okay, now it's going to get boring after that introduction. So the point here is systems will be able to write down circuits and mechanical systems and all sorts of things and write down equations like this. Okay? It's not easy to sit down and say what y is in terms of u. Actually, guess what? For this type of differential equation, you'll be able to do that later in the class. So you'll actually be able to write down y explicitly in terms of u. And when you see what y looks like, it's not simple. And you'll understand why it was that searching for a formula was going to take a long, long, long time, and that the right way to do it was to write down a differential equation. Okay. Enough of that. We should limit that sharply to about 5 minutes per lecture, and I think I just went over my limit. Okay. So back to differential equations. So this is a linear constant coefficient, ordinary differential equation. And there's a bunch of things here, like, for example, n here is the highest order of y, is called the order of the system. These constants are called the coefficients. And it turns out that when all the initial conditions are 0, a linear constant coefficient ordinary differential equation is actually linear. And you can check that directly. In other words, which is an interesting thing, because at the moment we have no real understanding of what this does. But we can actually say that it's whatever it is, it's linear, provided all the initial conditions are 0. And so this is a short version of what I said earlier, that what a differential equation does is it gives an implicit description of a system. It's not an explicit description saying, look, y is equal to this, and you write down some formula in terms of u. It's implicit. It basically says, no, I'm not going to tell you what y is in terms of u exactly. I'm going to tell you how y and its derivatives and u and their derivatives are all related. And then it's your problem to figure out the exact relation between them. Which, by the way, for this class of differential equations, you will be able to do. So let's look at some examples here. Well, you can have a dumb one where you have no derivatives at all. This is 0th order. And that's a scaling system, for example. You can have an integrator. An integrator just says that y prime equals, here, let me see if I can do it, something like that. That's close. Y prime equals, where do we go? There's y prime equals, I lost u. There we go. There, got it. There we go. There's y prime equals u. That's an integrator. Okay. You can have a differentiator, because you can have, if you have a differentiator. No, maybe this is right. I don't know. You have a differentiator, which says y equals u prime. You can have an integrator with feedback. That was our example just two pages ago, and that also satisfies that. So it's a differential equation. Okay. More importantly,
RC circuits. Here's an example. So here's a circuit. I have a voltage source going through a resistor and a capacitor. Oh. It's fun. It happens every 10 minutes or so. It's kind of...
Sorry, someone has tried to call in, so we're trying to get their audio to come up in the class.
Oh, okay. That's fine. Yeah. You can try some other stations. If it's fine. We'll see. Okay.
Hello?
Yeah.
Yeah, Professor Boyd, I can't hear you and I don't know whom to contact.
Well, it's certainly not me. Did our SITN people hear that?
I don't know. Well,
Okay. All right.
I'll let you continue then. Sorry.
Okay. Wait, if he couldn't hear me, how did he? Well, philosophical, there's a little logical question there that came up. All right. Okay. Okay. All right. So let's look at this. So you have an RC circuit. Well, the current flowing into this capacitor, it is it's simple to relate that. You have CV dot is the current flowing in, right? This is from 101. So V is actually, I called it Y here. So if we see Y dot equals I, but I, we know what the current flowing in here is. That's easy. It's this voltage minus that voltage. That's the voltage across the resistor, and then you divide by R, and that gives you the current flowing in, which is of course the same as this current. So we get this differential equation here. Okay. So you can rewrite this as a first order linear constant coefficient ODE, and it's RC Y prime plus Y equals U. So that's it, right? So this is an example where, for this circuit, you actually know, you could write down what the solution is, okay? But it's incredibly easy to write down a differential equation. In fact, this is basically just writing down KCL and KVL and stuff like that. Okay. Now here's a circuit that you did not know how to analyze in 101. It is a second order RC circuit. So it's a resistor, capacitor, and turns out here, in fact, this will make my point perfectly about how this works out philosophically. This circuit is kind of, roughly speaking, the analog of the two-body problem, right? There is an analytical solution. You saw it last quarter. Remember that there's like an exponential in there and all that kind of stuff and all that. So you saw all that, okay? Now, this one, okay? There's a solution, and it's not that hard, but it's not that simple either. And in fact, the right route is, what will be easy to do is to write down a differential equation that this circuit governs, okay? So let's see what it is. Well, the current flowing into C2 here is, of course, C2 Y prime. Well, that's equal to the current flowing through this resistor. But we can say exactly what that is. That's the voltage here minus the voltage here divided by R2. That's this, okay? Now, the current flowing here is also easy to say what it is. It's actually C1 V1 prime. That's the current flowing into this capacitor because we know the voltage across the capacitor. And that is precisely this voltage minus that voltage divided by R1. Okay? So that's this voltage. Sorry, it's this. That's the current flowing this way, and then I have to subtract the current that's the current that comes in here. Then I have to subtract the current that goes out there, and what's left over flows down into the capacitor. That's this. Okay? So now I take this equation, these two equations, like that, and I'm just going to eliminate V1. So V1, which I get from this equation, I express it this way, and I plug that into the second one, and I get this. I get C times Y plus R2 times Y prime, whole thing prime, because this is Y prime here. I get the whole, this is V1 prime, right, is equal to this. And I do a whole bunch of algebra here, and there's a lot of, it's not much algebra, a line or two of algebra. Very simple algebra. And eventually it comes out this way. It's R1 R2 times R2 C2 times Y prime prime plus R1 C1 plus R1 C2 plus R2 C2 times Y prime plus Y is U. So at the bottom of this page, I can't tell you what the solution of the voltage here is in terms of the voltage U. I can't tell you that. But what I can do is write down a differential equation. Now, soon you'll be able to look at this differential equation and say a whole lot about how Y depends on U. But at the moment, you can't. Let me also point out a couple of things about physical units here.
What's the physical unit of y and u? Amps, volts, charge, coulombs, volts. Okay. What's the physical units of y prime? Volts per second. What's the physical units of this coefficient here? Seconds, exactly. Okay, so this actually works out, has to be that way. What's the physical units of this? It's voltage acceleration. It's volts per second squared. And of course, look at that. You've got seconds squared. Okay. By the way, this is something you should simply learn to do, is do a dimensional analysis at all times. Always, just to check what's going on. Let me tell you what screws that up completely. Is every now and then, for fun, when we don't really care about doing a realistic example, but we just want to work something out, a common tradition, I don't have any problem with it, is just to make all the coefficients 1, right? Then what happens is it screws up all your dimensional analysis, because everything in sight is like, is 1 ohm, 1 volt, something like that. Okay, here's another system which is actually going to play a big role in a lot of what we're going to do, and it's actually something you'll leave the class having a very thorough understanding of. It's a mass spring damper system. So actually, how many people have seen an analysis of this anywhere, like in some physics class or something? Because this is one of those things where you should see it. This is something where you should see it 3 times. That's the expected number of times. That's the right number of times to see it. And it's worth it. It's actually worth understanding how it works. Not actually so much because one day you'll be walking along and you'll see a mass spring damper. Because what's going to happen in this class is you're going to realize that once you understand the dynamics of this, it turns out you actually understand the dynamics of, well, as we'll soon see, a vast array of things. You'll see that. Okay. So where does this come up? Well, it can be a very simple model of an automobile suspension system. So that's the mass of the vehicle. This is the shock absorber, and this is the suspension spring or something like that, suspension system. And I should explain what these bits are. This is a spring here. It's a linear spring, meaning that if the spring is relaxed, there's no force, but as you scrunch it down, it makes a force which is proportional to how much you've scrunched it, right? If you pull it, it pulls back, and it pulls down with a tension proportional to how far you've pulled it away from its rest position, okay? Now the damper here is a different thing. That's like a shock absorber. And what this does is it puts no force at all for a given displacement. So if you take a shock absorber, you can get these. It's not an automotive one because they also have a little spring inside. But a typical one, in fact, the reason this is drawn like this is it's often here's an old timer term. If you want to, like, I don't know, connect to your the 70+ crowd in mechanical engineering. It's called a dash pot. A dash pot is this pot of oil, and it's got like a kind of a piston here with leaks around the corner. And so all of you can understand what happens if you take a pot and stick oil in it and then put a piston with leaky sides. You all have the intuition of what happens. If I put it to a certain position, right, as long as I'm not moving, there's no force of any kind on it. I mean, forget gravity for now, right? But what happens if you try to move it? Well, in fact, the force is it depends on all the thermodynamics and the fluid mechanics and all that. But there's a force which is dependent on the velocity, right? So in other words, that's your model here of a dash pot. This is a simple one in that the force opposing is proportional to the velocity, okay? And that's accurate for some situations, okay? So that's it. That's called the damping force. And that's proportional to, so here's the model here is you have a spring. And what we do is in this, the way I've drawn this model, the input, in fact, is the ground displacement. So this could be an analysis of a suspension of a vehicle, which is moving, and the effect of that is that the ground, these are so if you have a pothole, U goes like that, or something like that. If you go over a curb, U goes like this, it's 0, and then in fact it's a step function, so it just pops up, that's a curb, and so on. Okay, so all of these, a ramp function, if U is a ramp signal, that means that you're taking the car or the vehicle and you're driving level, and then at t equals 0, you drive up a hill with constant slope. Okay? And you should even, by the way, have some physical feel for what this thing will do. If you go, for example, if you go over a curb, what will this do? Suppose U, there's no equations now. Well, there's some differential equations here, but that doesn't, no, not yet, not even yet. If U looks like that, what will Y look like, the displacement of that mass? What happens if you drive a car over a curb? Yeah, okay, so, I mean, what happens out here? Well, nothing, because you're just driving on level ground. All of a sudden, your wheels pop up 6 inches or something like that. What happens, does your mass pop up instantly or what? No. What in fact, so what happens if I draw the displacement of the mass? What might it look like? It might look something like this. You're saying it might actually do something like that, right? Where does it settle down to? If you drive over a curb, which is now 6 inches higher, where does the vehicle height settle out? 6 inches higher. Sure. Okay? So anyway, what this says is we haven't written any, we've written no differential equation of any kind. No analysis, nothing. But the point, it's very good to keep an intuitive feel for this, because otherwise everything we write down is just equations. So anyway, this is the picture here, something like that. That's what might happen. And we'll see that's pretty much right. Actually, you probably wouldn't want this in a vehicle, because you'd probably get sick to your stomach or something like that. So what you would probably want is something that makes one bump up and then settles down, or even one that kind of just goes like that. But we'll talk about all these things. So that's the picture. Now another way, if you want another way to visualize this mass spring damper, is it's the response of a building in an earthquake. Here it's actually not so much vertical, it's actually horizontal. So basically you take a large building like the one we're in, and you grab the ground under it, okay? And you take the ground and you move it rapidly left and right, like that. And then the building, which is not completely stiff, is going to kind of do this. If it's totally stiff, it just kind of moves back and forth, right? But it's not. It'll kind of wiggle and stuff. And in fact, you could easily get something that looks like this. Now, the picture there is that this is usually horizontal displacement, not vertical, as it is in a suspension system. But we'll see that this just comes up in a lot of places. It's a very good thing to know about. Okay. So that finishes up our sort of overview of some systems. We'll see a lot more before this quarter is over. And we're starting another topic now, which is a big topic. It's the Laplace Transform. And ideas related to this you're going to see from now on, not just in this class, but in lots of classes. So this is it. It's Laplace Transform. And so and let me first say some background, although I've already exhausted my philosophical background limit for the lecture, for today's lecture. Let me just say a little bit about it. The basic idea is it's in the spirit of some of the stuff you did in 101. In 101, you looked at steady state sinusoidal circuits. And what happened there was things like resistors and inductors, which in fact are described by differential equations, right? That's what if someone says, what does a resistor do? It's described by sort of algebraic equations. What does a capacitor or inductor do? It's described by differential equations, okay? So we're not going to get away from the differential equation thing. They're out there. But in 101, something very clever happens, which is you say, if all the signals are sinusoidal, then a capacitance or an inductance looks like kind of a resistance. It's a bit hokey because the resistance is complex, and the currents and all that are complex. So there's something not involved very hokey about this, but the advantage, and we call it impedance then instead of resistance. And of course, you have various problems then, because if someone comes up in back of you while you're doing steady-state sinusoidal analysis, and someone says, what are you doing? You say, oh, I'm figuring out what the voltage is in the circuit. And you go, oh, what's the voltage? And you go, well, it looks like it's 1 plus 3j. And they say, what does that mean is 1 plus 3j? How could the voltage be imaginary? I mean, it doesn't make any sense, right? So, but the nice part is, aside from these weird ideas that now things are complex, and provided you can actually answer that question, then you have a long story. You say, well, okay, look, no, truthfully, the current and voltage here is really sinusoidal, but I'm kind of representing it as this complex number and blah, blah, blah. The person who asked the question is still there, and you can go on. Then you say, look, what I'm doing is I'm solving, I'm cheating. I'm actually solving a complex system of differential equations, but I'm doing it using complex arithmetic. I mean, that's the real answer. Okay, so it's that spirit which motivates the Laplace transform. It's the exact same idea. And so we'll see that. So the idea is it's a general transform. It's going to convert integral and differential equations into algebraic equations. That's exactly what's going to happen. So it's just like phasors in sinusoidal steady-state analysis, except for a couple of things. First of all, it's going to apply to completely general signals. It's not going to apply just to sinusoids. Okay, totally general. And it's going to handle non-steady state conditions. So we're going to be able to figure out all sorts of things that you couldn't in 101. Okay? It will, of course, reduce to phasor analysis, which we'll see later, if all the signals are sinusoidal. But it'll handle any type of signal. And so it'll allow us to analyze all sorts of things, like linear constant coefficient ODEs, very complicated circuits with sources, inductors, resistors, capacitors, very complicated systems with integrators, differentiators, gains, all sorts of things. Complicated mechanical systems we're going to be able to understand and analyze. Okay? Okay. So what is the Laplace transform? Time to say what it is. First of all, we're going to be interested, when we talk about Laplace transforms, we're going to be interested mostly in signals defined only for t positive. Okay? So in terms of differential equations, these are often what are known as initial value problems, right? So we have a big mechanical system, an electrical system, or an electromechanical system, or something like that. Or it could be, by the way, an economic system. We don't know. We have some differential equations or dynamical system. And what we're interested in is what's going to happen in the future. And so we simply relabel our time axis so that t0 is the beginning of the time at which we're interested in. Okay, so that's all t equals 0 means. It means the first time in which the time after which we're interested. Okay. So the Laplace transform of a signal is the following function. It is defined this way. So f is a signal. It's a function that accepts a real non-negative argument and returns a real number. And the Laplace transform is another signal, except that its argument is a complex number. And it's defined this way. You take the integral of f of t e to the minus st dt, 0 to infinity, and that gives you f of s. Okay? Now the left and right-hand sides here these are complex numbers. It's for a fixed x, s. The Laplace transform of little f is this function big F. Okay? Now, again, I promised I wouldn't do this again, but I don't know. I promise a lot of things and then do it again anyway. So we're going to go back to C to imagine how incredibly complicated the Laplace transform is. Okay? It is a function, and it accepts as argument a function of a real variable that returns a real variable. Everybody with me? Okay? Then it returns a function. That's a function which accepts as argument a complex variable and returns a complex variable. Everybody with me? Doesn't matter if you're not. I mean, you can also, if you like, you can also just do this informally and just say, oh, okay, well, that's the formula defining the Laplace transform. Okay? So a couple of important things here. First of all, the units, which is never discussed. You see t is time, and s is this Laplace transform variable. Its units, its physical units, are frequency. It's inverse seconds. Okay? Otherwise, e to something doesn't make any sense, which you would know, for example, if you really wanted to understand why that was true, you look at the power series expansion for e. It's 1 plus something squared over 2 factorial plus something cubed. So there's no units you can assign to that something that may have that make any sense at all unless it's unitless. Okay? So s has the that's called a complex frequency variable, and its units are inverse seconds. It's frequency. Okay? And so it's actually important to understand that when someone says large S, you should think fast. That's what it means. Large S means fast. It means large frequency. It means either rapid oscillation or rapid motion. That's it's right. It means 1 over S is very, very large. Okay? Sorry, S is very, very large. Right? So it means that the associated times, which is 1 over that, are very, very small. Okay. So t is the time variable in seconds, and st is unitless. Okay. So here's a very common notational convention. That when we have signals given by lowercase things, their Laplace transform will be given by the same symbol but capitalized. That's the only difference. Okay. Now this is just a convention, and sometimes people don't follow it, but it's kind of the idea. And I think you have a convention not unlike this with phasors in 101. Is that right? Is that the kind of the convention you did? So you had little v was, if someone says what's little v, the answer would be, oh, it's cosine, 2t plus 3, right? And then someone asks you, well, what's big V? That's that's the phasor, that's the complex number. Is this the convention you used in 101, approximately? Okay, so same story here. So that's the idea. It's a convention, and of course, like all conventions, it's kind of useful when everyone understands the protocol. When if there's any question, though, of course, the right thing to do is just ask. So let's work out an example of the Laplace transform. Here it is. Function e to the t. Now what we really mean, of course, is well, it's e to the t. If I ask you, remember everything here, we only care about signals defined on t bigger than or equal to 0. So if I say what's f of minus 1 here, what's the answer in this context? What is it? It's undefined, right? I mean, the correct answer is not to say 1 over e, which is about 0.38. That's wrong. The correct answer in this context is to say f of minus 1 is undefined. Okay? So it's Laplace transform. We just plug it in. It's e to the t. Now you multiply by e to the minus st dt. And I have to integrate with respect to t. So I get this exponential. Now that's a complex number. And, well, I know how to integrate this. I get it's this divided by this coefficient. And I have to evaluate that at infinity and 0 are the limits. Okay? Now, when t equals 0, there's no issue as to what this is. That's very simple. It's precisely equal to 1 over 1 minus s. End of story. Now, what about t equals infinity? Well, what is e to the 1 minus s times t as t goes to infinity? Well, that's complicated. Okay, you have to know what's the magnitude of e to the 1 minus st. It depends on s. It's the real answer. Okay. Now, e to the 1 minus st is equal to e to the minus j times the imaginary part of st. That's a complex sinusoid. You know this from 101, right? Its magnitude is 1. Then you get this thing, which is e to the 1 minus real part of st, absolute value. Now, as t gets big, and you look at e to the something times t, if that something is negative, then e to the something times t, as t gets big, gets really small. It not only gets small, it gets small, real fast, right? That's this thing. On the other hand, if this thing's positive, this gets real big, real fast. It's a real exponential. So here's what happens. This is so it says that as t goes to infinity, the upper limit here, 1 over 1 minus s times e to the 1 minus s, that goes to 0, provided the real part of s is bigger than 1. Okay? That's what it is. It goes to 0, provided the real part of s is bigger than 1. So really, to be very careful here, I should say something like this. This is for the real part of s bigger than 1, and this is sort of it should say undefined otherwise. Okay? And if we were doing things very carefully, this is what we would have to write. We would have to write this. Okay. Now, it turns out this is always true for Laplace transforms, right? There's always some s's for which the formula makes sense, and a bunch of others for which it doesn't. Well, it just gets kind of tiring to write this kind of thing down everywhere. Not only does it get tiring to write this down every time you take a Laplace transform, but it turns out actually to not have any particular use. In other words, it never changes the answer, writing this down. So what happens is there's many ways to describe this. You can describe it as sloppiness, or you can describe it as informality. But what we're going to do is we're just going to say that the Laplace transform of e to the t is 1 over s minus 1. That's what we're going to say. And we're going to suppress all this this legal, basically so in a legal proceedings you would have to say that the Laplace transform is equal to 1 over s minus 1, provided the real part of s exceeds 1. Okay, but otherwise it's undefined. Okay, it turns out we're not going to do that. We're just saying it's 1 over s minus 1, and that's kind of the end of that. Now, there's actually a way. This informality actually makes a lot of sense you can also justify it using actually some pretty fancy math. And what it's called the analytic continuation. If you know what I'm talking about, fine. If you don't, that's fine too. So what it is to look at the formula and say, that formula there, it actually makes sense for s, for s equal to 0, for example, right? This formula makes sense. When s equals 0, this is equal to minus 1. Okay? On the other hand, the integral, when s equals 0, this is the integral of e to the t dt. What's the integral of e to the t dt? What is it? Oh, it's plus infinity. There's absolutely no question there. There's no choice. I mean, that makes perfect sense. Integral e to the t is perfectly well defined. And the only possible value it can have is plus infinity, period. Right? Okay. So we have a little bit of a problem here. I think you can see this, right? Because if I plug in s equals 0 up here, I get plus infinity. If you plug in s equals 0 in this formula, you also get something, right? 1 over s minus 1, and when s equals 0, there's no question as to what that means when s equals 0. It means minus 1. It's minus 1. There's no discussion about it. It's minus 1. So the point is that this expression down here is correct. This is, you know, I'm just showing you, this is the distinction between sort of the legal, the way you would describe this legally, and the way you would do this informally. Okay, so that's going to be our approach here, is that we're going to be informal about it. Probably a few more times I'm going to mention things about where the Laplace transform makes sense and where it doesn't. What you'll quickly figure out is it doesn't make any difference. Okay. However, it's good to know this because, you know, someday your roommate or somebody might be looking over your shoulder, might look at this formula, and then quite innocently plug in s equals 0 in this formula and get a number, which is plus infinity. Quite innocently plug in s equals 0 down here, get another expression number, which is minus 1, and then he or she would point out to you that minus 1 is not in fact equal to plus infinity. Okay? So at which point, depending on whether it was before or after the drop date, you could drop the class or whatever. So I point this out just because it might happen. Well, actually, it's going to turn out in practice that this is not an issue. But I point this out just in case to save you some embarrassment, possibly later when your roommate points this out to you. Okay. So we're going to be informal. We're going to say the Laplace transform of e to the t, 1 over s minus 1. But there's caveats here, which is, watch out. You plug in an s for which the integral doesn't make sense, and you're going to get some fishy conclusions, like the one we just came to, which is plus infinity is equal to minus 1, which is something I bet you didn't know before. Okay. Okay, well, let's look at some more examples and see how this works. Let's look at a signal which is 1 for t bigger than or equal to 0. It's just a constant. Now we have to take f of s is the integral of 1 e to the minus st dt, and you get, again, minus 1 over s e to the minus st. Again, this formula makes sense for real s positive. Okay, but the formula makes perfect sense for all s except s equals 0. Okay, so once again, you would have the possibility of embarrassment by a sort of, I don't know, a careful roommate or somebody just casually overlooking this, and so on. In fact, to cause embarrassment. In fact, actually, now that you know this, you can embarrass anybody else you know. In fact, find like a senior in electrical engineering. In fact, that's what, we'll quit that way. Here's what you do. Go find a senior in your dorm in electrical engineering. Okay? Someone asking me if you had 101, I say, oh, years ago. You use that material all the time. 102, sorry. You use material all the time. You go, great, because I have a really simple question for you. You watch what happens. And you go through and say, I'm a little bit confused. What's the Laplace transform of, like, e to the t? And I'll say, everybody knows 1 over s minus 1. You go, oh, great, okay. You go, what's that when you plug in s equals, like, 0? Minus 1, what do you mean? Then you say, what's the definition of Laplace transform? Just try this, okay? And we'll report back on Friday what happened.